2.7 is a continuation for what we did in 2.6, where we started talking about rational expressions. In particular, in 2.6, we talked about simplifying rational expressions, and we talked about multiplying and dividing rational expressions. So what we're going to talk about in 2.7 is adding and subtracting rational expressions. To be honest, adding and subtracting rational expressions is a little bit more challenging than multiplying and dividing. So last time, like I said, we looked at simplifying, including multiplying and dividing. We found that the process that we used for fractions with variables works the same way as for fractions without variables. And the same will be true today as we add and subtract. It will be much the same. So as we're taking a look, I didn't get these cleaned out. Okay, so we're going to find least common denominators. We will need common denominators when we add or subtract fractions with variables, just like we did when we had fractions that didn't have variables back in section 1.4, I think it was, or something like that. So as we're taking a look at these, you might notice that the denominators both have an x in them and they both have a 10 in them, and you might be led to think, well, they're quite similar. The problem that we encountered when we were simplifying will present itself here again. Unless they match completely including their sign, they don't match at all. We need factors that match, not just terms. So this one has lots of terms that match, right? The x matches, the 10 matches, but the factors, that means considered all of them at once, don't match because the signs are different. So when that happens, your least common denominator is simply the two denominators multiplied. So x plus 10 and x minus 10. Now, for the most of what we do, there's really no reason to multiply that out, kind of like those ones that you were talking about before, Anya, like should I just distribute all them back out? It's not that you can't, it's just that it doesn't really lend you any new information. It doesn't lead you anywhere to begin with. So typically speaking, we'll leave them in factored form, which is great because that means less work, okay? So this would be our least common denominator when the denominators flat out don't match, and they don't here. Now, on the next ones, we're actually going to add and subtract, but sometimes the denominators will either match completely, like they do on number 2, or they'll almost match. Let me show you an example real quick. Let me flip through it, like they do on number 6. Right? One's a 3a and the other one's a 3. They're definitely similar, but there's something slightly different. So just like with fractions without variables, if the denominators completely match, we can simply add straight across the numerator. So the denominator will stay the same, it's 5x, and I would add 8 plus 6 to give me what? 14, yeah. So it'd be 14 over 5x. Now if the 14 and the 5 could reduce, we would reduce it at this point, but these don't. So we're done. So I know sometimes it's tempting to think, I'll just remind you of this fact, although we know we've already talked about it, but it's been like 2 months or something. It's really tempting to add across the top and add across the bottom. But you want to think of it kind of like what you would do if you were talking about a pizza, right? Most pizzas are split up into a certain number of pieces. We'll say 8. Little Caesars does 8. So if you split the pizza into eighths, right? If I eat 1/8 and Cole eats 1/8, we did not eat 2/16, right? We ate 2/8 of the whole pizza. The denominator doesn't change. So the same is true for this. On the second one, number 3, the second one on the screen, but number 3, again, the denominators match. So the denominator will stay the same. It's y minus 5. And then your numerator this time will actually have subtraction in it because there's a minus sign between there. So I have y minus 2. And again, I know it's really tempting to say, hey, look, the y's match. Boom, boom, I'm going to cancel them out. You can't do that, and let me remind you why. Let's say that you had 5 plus 2 over 5 plus 3, right? It's not appropriate to just cancel out the 5s. You have to do the addition part first. I think the reason that it feels different when we look at this is because the 5 and the 2 actually have the ability to combine into something simpler, whereas the y and the 2 or the y and the 5 on the denominator don't. So we are stuck right here, and that is the simplest form that we have for the problem. But that's good, right? Less to simplify, less work to do. 4, same kind of thing. Denominators match. So we will combine with the same denominator. Now on this one, it starts out with 9x minus 3y. But then it has a subtraction sign here that has to apply to each piece. So I would end up with minus x, and then I would end up with positive 10y. Okay, I have to subtract everything in the numerator that follows. So everything from the second numerator gets the negative attached to each piece. Okay? And then I will combine like terms. So I have a 9x and a negative x, which gives me 8x, good. And then I have a negative 3y and a positive 10y, which gives me positive 7y. And all of that is over the denominator 2x. Again, you might be tempted to say, hey, that 2x and that 8x, I mean, they have things in common, and they do. It's true. But the 7y doesn't. So unless the denominator has a component that's common to each part of the numerator, I can't reduce or simplify anything. I'm stuck at that point. So there isn't any reducing from here that I can do. I'm finished. All right, number 5, same denominators again. So we have z squared plus 7z plus 12. And this is addition, right? So I'm going to add my numerators. So I have z plus 3. So I'm trying to sort of hit the pitfalls that you might encounter if you haven't noticed. It's really tempting. It's really tempting on this one to say, hey, look, nothing cancels, I'm done. The problem is that the denominator might be able to be factored. We don't know. We haven't had a denominator that's got a quadratic in it before this one on this lesson, right? So we need to factor the denominator just to see if it might have a z plus 3 in it. It might not, and we might be done, but it might, and then we're not done. So we're going to attempt to factor that denominator and see if there's any reducing that can happen. So the denominator is a fairly friendly one because it's got a coefficient of 1 in front of z squared. So I'll have z and I'll have z. 12 is not such a friendly number to end with because I can multiply 1 times 12, 2 times 6, or 3 times 4. I have lots of options. So it's not the most friendly number to end with. However, the signs are friendly. I have signs here that are both positive, right? So that means my signs have to all be positive because everything's positive in the original expression. So I need two numbers in this list of numbers, 1 and 12, 2 and 6, or 3 and 4, that multiply to 12. Well, all of them do that, but they add to 7. So what two numbers would that be? Yeah, the 3 and the 4. So a 3 and I have a 4, and lo and behold, I do in fact have a z plus 3 in the denominator that will cancel with the z plus 3 in the numerator. Now what you want to remember is that when you cancel between the numerator and the denominator like that, you're still dividing. So when I divide the numerator by the same thing that's already in the numerator, I get the number 1. And the denominator will still have the z plus 4 in it. So again, it's tempting, and I sometimes see students do the cancellation, everything looks great, but then they forget that that z plus 4 is in the denominator, and there's a 1 in the numerator still. Okay? You can cancel the z plus 3, and the reason that you can is because they are factors, right, multiplication pieces that match. Instead of terms, addition and subtraction pieces that match. It's about the fact that they can be multiplied by what's there. Yep. Okay, so I already sort of mentioned problem number 6 before when we were talking about least common denominators because they are close, but they're not exactly the same. So all the examples I've had before, problems 2 through 5, all had common denominators. We just added across the numerator or subtracted across the numerator, kept the denominator the same, and we were done. Problem, of course, with number 6 is the denominators don't match. But they're easy to get to match. One's 3a, the other one's 3. So the 3's match. There's no addition and subtraction, notice, right? No addition or subtraction. The 3's match, but I don't have the variable. So I need a variable to be in the denominator here so they match. But if I multiply the denominator by something, in this case a, I have to multiply the numerator by a as well. So this changes the expression. You don't necessarily need to write this down, but if you feel like it's useful, then definitely you can. It changes this expression to say 7 over 3a minus 2a over 3a. That's what I really have. And then it looks just like the other problems that we were doing before this. Denominators match. So the denominator stays the same. And I simply subtract, in this case, because it's subtraction here, right? The numerators. So it's 7 minus 2a. And again, it's kind of tempting to say, hey, there's an a in the top and a in the bottom, I can cancel it. But there's not an a on every term in the top, so I can't cancel it. There is nothing on the top and the bottom that are the same in every single piece, so I'm done. Okay, so 7 has denominators that are just slightly more different than 6. What do they have in common? The x's, right? So it's not like the very first example that I did where there was addition and subtraction. I had to actually multiply the denominators by each other. I don't need to multiply 7x times 6x because they have the x's in common. There's no addition or subtraction involved, right? They have the x's there. But they don't have matching coefficients. And 7 and 6 don't have anything in common factor-wise, right? I can't divide 7 and 6 by a common factor. So my best case scenario here then is to multiply your first denominator by the coefficient that it's missing. And if I do it to the bottom, I have to do it to the top. And the second denominator by the coefficient that it's missing, and if I do it to the bottom, I have to do it to the top. So I'm going to do an intermediate step here. Again, you don't necessarily have to show it, but if it's helpful, please do. What is 6 times negative 5? Negative 30, right? Over, and then 7 times 6 would be 42x. It's addition. 1 times 7 is 7, and it's over 42x. So this is the point when it looks just like the values that I was doing before. They have matching denominators. So I'll add across the top. I have negative 30 and positive 7. What does that give me? Negative 23. The denominator is still 42x, because that's the denominator I have from the pieces before. And then I would look and see, because there's no addition or subtraction on top on this one. It actually simplifies to something that doesn't have addition or subtraction. The other ones have not necessarily always done that. But 23 and 42 don't have anything in common. 23 is a prime number. If you weren't for sure, you could just try all the factors below it and find very quickly that they won't divide it. But we would try, right? They don't have anything in common here, so again, I'm done. Any questions on that one? Okay, let's try another one. Again, the denominators are sort of close. They both have a d in them, right? There's no addition and subtraction. If you really wanted to, you could multiply the 4 and the 8, right? Multiply the first one by 4 and the second one by 8. You could do that. But it would be overkill. Because 4 and 8 have something in common. What do 4 and 8 both divide by? They both divide by 2. They also both divide by 4. Right? So if I were thinking about like lists of multiples, like let's do multiple lists. I haven't ever kind of written it this way before, but it might help someone, so I think I might do it just this time. If we're thinking about multiples lists, if I wrote down 4, 8, 12, 16, right, list of multiplication factors, and I did the same thing for 8. I did 8, 16, 24, and so forth. The least common multiple is the one that shows up first in the list, and it's actually 8. If you don't find a least common multiple and you just find a common multiple, it's okay. You just have more reducing to do at the end of the problem. Won't hurt anything. But what it means over here in my problem is that I really don't need to get anything bigger than an 8, because 8's the least common multiple of 4 and 8. So all I really need to do is multiply 4d by 2, and I will get the 8d that's in the other problem. And again, if I do it to the denominator, I have to do it to the numerator. So the first fraction doesn't change. It's 9d minus 1 over 8d. And then the second one, I need to distribute the 2 across. So it's actually 4d minus 6 over 8d. Okay, so we're going to combine all the numerator together because the denominators now match. I have 9d minus 1 plus 4d minus 6 over 8d. How many d's do you have? 13d on top. And what about my constants? Negative 7 over 8d. So they don't all have d's in them, so I can't cancel the d out. And 13, 7, and 8 don't all divide by a common factor. So the numerical values themselves also don't reduce. All right, the last one is the most interesting. It's closest to where we began our problem, which is finding a least common denominator on an x plus 10 and an x minus 10. This one's most similar to that. These two denominators sort of look like they might kind of match. They both have an x in them. But what makes this one different than the other ones is that there's addition in the denominator of one of them as well, right? And that's a big thing, because it no longer means that I have factors, that I'm just looking at these pieces matching. I actually have terms. The individual pieces separated by addition and subtraction are terms, and I don't need terms to match. I need the whole thing, the whole factor to match. So it's much like having an x plus 1 piece and an x piece and saying they don't match because they're not the same factor. So it means, like on problem number 1, my least common denominator is the two denominators multiplied. So x plus 1 will be multiplied by x, top and bottom, and x will be multiplied by x plus 1, top and bottom. So I'm going to leave my denominator in factored form because it's possible it might reduce later on. And if I multiply it back out, then I might have to factor again. So I'm going to leave it in factored form, at least to check to see that there's no reducing. This 7 will distribute through the x plus 1, so it'll be 7x plus 7. Sorry. Then my other one is also an x plus 1 and an x. And then my numerator is a 6 times my x, so 6x. If you don't want to write down that step, you just wanted to skip to the step I was about to skip to, that's fine too. X and x minus 1 in whichever order, x plus 1, sorry. So we have 7x plus 7. And then I have minus the 6x. Okay, how will the numerator simplify? X plus 7. My denominator has an x in it and an x plus 1 in it. There's no factors that cancel, though. I know there's matching terms, but remember, we can't cancel term-wise. We can only cancel if the factors match. And the x plus 7 on top does not match the x plus 1, essentially on bottom. So we are stopped at that point. If you wanted to distribute out the denominator, you could. It wouldn't be wrong. It's just also not necessary. Okay? Any questions on that one? Okay, so you guys have about 15 minutes. Let's take a look then at your homework number 19. It'll be due on Thursday. Actually, do we have a quiz on Thursday or is it on next Tuesday? I don't remember now. Tuesday. So there's also a quiz coming up next Tuesday that will include the homework for this. But we have a homework homework 19 that we would be working on now.